This is the final of our 3 videos looking at tutorial problems from the vectors, notes, and for mechanisms and structures. We're looking at problem 3 in this video, and we'll take the same approach we've taken in the previous 2. We're going to represent our system as an accurately drawn scale diagram with the correct angles and forces drawn to scale, and we're going to use our method of graphically determining the resultant and the equilibrium. So this time for question 3, we have a 15 Newton force and a 30 Newton force. And again, this means that we couldn't use a scale of 1 centimetre to 1 Newton. It might just about fit in our paper, but we would be pushing it. So instead, we'll use a scale of 1 centimetre to 3 Newtons. So this is for, I should say this is for question 3 here. And our scale will be 1 centimetre is going to be equal to 3 Newtons, which means we're going to have a 5 centimetre line and a 10 centimetre line. So we divide by 3 to get the number of centimetres we need to use, and we'll measure our angle between them. Our life is made slightly easier this time because the 30 Newton line is horizontal, so we only have to measure the angle up from there, but we'll still take great care to make sure we do everything correctly. So I will still draw a little cross to be our starting point, but what I'll do differently is I won't draw a dashed line this time because we're going to have a horizontal line on our page. So I'll draw our 30 Newton line first of all. This line will be 10 centimetres long and it will be completely horizontal, pointing to the right. So if we line up our ruler with our starting point, and we can then draw a 10 centimetre line. So we have our first vector drawn in here. And again, we always put a little arrowhead on our vectors to show the direction. We're going to measure up 75 degrees from this line to draw it in our second vector. Line up our ruler with the starting point, and this vector is 15 Newtons, so in this scale will be 5 centimetres long. And we can put these values on our diagram. It's 15 Newtons, that's 30 Newtons over there. And this angle is 75 degrees. We'll repeat what we did last time. We need to mark in our angles again to complete the sides of our parallelogram here. So we'll get a nice horizontal line coming out of the end of the blue vector from that arrowhead. And this will be a 10 centimetre line starting at this point. So just line it up and then draw 10 centimetres going to the right. And then we'll do the same with our second vector. Make sure we've got an angle pointing up at 75 degrees. That lines up with the ends and it's 5 centimetres long. And we can draw in a line here, completing our shape. And again, giving us the end point of our resultant. So where these two arrowheads come together, the blue arrowhead and the red arrowhead, that is the end of our resultant. So we're going to get a ruler out again. We're going to join the starting point to the ending point. Our starting point is the cross we drew at the beginning. Our ending point is where we've just brought these two lines together, and we'll just adjust until we have got it lined up. And this looks quite good. And again, just for illustration, I'll take a different color and draw our resultant vector here. The same things as before, we need to measure the direction of it and we need to measure the size of it. So looking at my ruler here, I make that to be about 12 1/4 centimeters. So that's what I'll write down in a second. And the angle up from the horizontal, we can see that on the screen because of this ruler we've got here, is 23 degrees. So I can write all of this down. So we have a 23-degree angle and a magnitude, I'll write this down here, for a resultant magnitude of 12.25 centimeters. I think that's what I'll just double check that before I. Yes, 12.25 centimeters. And of course, every 1 centimeter is 3 newtons. So that's going to be 36.75 newtons. There's almost certainly there's no way as accurate as that. So we might just round that to 36.8. Depends how confident you are in your measures. If you can measure to the closest, we can probably measure to the closest millimeter. So we can probably say with the best we can give it 36.8 newtons. Around that. That's the accuracy we can get. And the direction, of course, we have that ready. A direction up and to the right, an angle of 23 degrees up from the horizontal. And I'll quickly move that over because I, of course, need to draw in our equilibrium, which is not going to fit if I do that. So I can squeeze that in there. Our equilibrium, and exactly as before, it needs to be the same size of line. So from this starting point, we're going in the reverse direction from our resultant with the same distance. So it'll be the same size of vector, 36.8 newtons. And if we're to draw in a horizontal line here, we're coming down at an angle of 23 degrees. And we could write all that as well. For completeness, we would write the equilibrium has a magnitude of 36.8 newtons and is acting in a direction of 23 degrees downwards from the negative direction of our horizontal line. And that concludes the solution to question 3.